Okay, now as for this graph, so if I want to take a cube of ice and start with a temperature of minus 20 Celsius, right? It's been in the freezer for a while. I take it out of the freezer and I add the heat source. This heat source has a certain power, so let's say it's 100 watts. So it's giving this ice cube 100 joules every second. So what's going to happen is the ice will only start to melt after it has reached a temperature of 0 Celsius, right? So if I want to plot temperature, so we started with negative 20 here, against heat, or you can say time. So we're giving 100 joules every second. So you can count the seconds, or you can count how many joules. So you can have 100, 200, 300, 400, 500, or 1 second, 2 seconds, 3 seconds, 4 seconds. It's the same thing. Let's say we start with heat, right? As you're starting to add up heat, temperature of the ice is going to increase. So the more heat you're adding, more joules you're going to be adding to the ice, the more the kinetic energy now of the particles will start to increase. They're going to start to move a lot faster until they reach a temperature of 0 Celsius. So it's going to increase until it reaches 0 Celsius, right? This amount of energy, so if we have heat, we can calculate this amount of energy. If we know, so how do we know how much energy is required? So if I'm telling you, I want to heat up an ice cube from negative 20 Celsius to 0 Celsius, what do you need to find the energy required? So you should know that the equation to use is E equals mc delta T. So you have the delta T, which is 20 Celsius. You need the C of ice, you need the mass that you're using for this whole experiment. So let's say we're talking about 1 kilogram of ice. So if you go to your books, the C of ice, specific heat capacity of ice, is 2100. We know that the difference in temperature is 20 Celsius or Kelvin. The joules per kilogram Celsius. Then the mass, let's say, is 1 kilogram. That is enough for you to calculate how much energy you need. So then energy is, so to heat up each kilogram of ice by 1 Celsius, you need 2100 joules. So if you needed to heat it up by 20 Celsius, then you need to multiply that by 20. So you need 42,000 joules. So you either have 42,000 joules here, right? Or if you want the time instead, so you have the power equals energy over time. That's going to take you, so time is equal to energy over power, which is 420 seconds. So you either have 420,000 joules or 420 seconds if you have the time. It's the same thing. Now, we've reached a point now where the ice starts to melt now. So how much time, we know that now the temperature is not going to change, because now the energy that you're putting in, or the heat that you're putting in, is not going to increase the kinetic energy of the particles. So your temperature is not going to change until the whole ice has melted. So now you want to melt a block of ice and you want to turn it into water. So how much energy do we need for this? Now we want to talk about latent heat. So you have 1 kilogram of ice. You need to know what is L of ice of fusion, right? Latent heat of fusion. Again, if you look at the books, ice has a specific latent heat of fusion of 330,000 joules per kilogram. So each kilogram of ice, in order to melt it, you need this many joules. So if you look this up, so it depends on the question. If sometimes you're given that, sometimes there are certain things that are unknown. You want to find the latent heat. It's different, but I'm trying to do this in a different way so that I'm hoping this will help you understand it a bit more. So this is the actual latent heat of ice. L, by the way, is energy over mass. So if we're talking about 1 kilogram, so energy is equal to L times M. We know that the L is 3,000 joules per kilogram. We know that it's 1 kilogram. So the energy required is this many joules in order to melt the ice. So you add 330,000 plus 42,000. You will get, so the total energy here that has to be here is 200,000 joules, right? Or if you need the time, you can calculate the time since you have the power. So you're going to have 372,000 seconds. So this will be 330,000 joules, or 3,300 seconds if you're using a 100 watt heater. So if I'm adding a heater here that's 100 watts, it should take it 3,300 seconds in order to melt fully. So it's gonna go all the way up to here. Obviously this is not properly scaled. If you wanna draw it properly, then we can draw it properly. So now here, the whole ice is melted. Now it's all water. So now we have here solid, ice, solid and liquid. We reached this point where it's just liquid now. Now we have fully liquid. We wanna heat that liquid from 0 Celsius to liquid of 100 Celsius. We need energy to do this. So how much energy do we need? Now we go back to the specific heat capacity of water. And the specific heat capacity of water is 4,200 joules per kilogram Celsius. What is the amount of energy that you need? MC delta T. Delta T now is 100. C is 4,200. Mass is again 1 kilogram. So you can calculate how much energy you need. So you need 420 kilojoules in order to heat up 1 kilogram of water from 0 Celsius to 100 Celsius. So now you need to add this number to this number to know where we're reaching here, right? It's gonna give you, so here you have to have 792 kilojoules, right? Or 7920 seconds time required. So then you want to reach 100 Celsius. Let's say 100 Celsius is over here. This is how it's going to look like. Now here it's going to be just pure liquid, right? When it reaches 100 now, what's going to happen? Now I want to know the amount of energy it requires to go from fully liquid all the way to vapor or steam. So you need more energy, and it's going to be latent, right? It's going to stick to 100 Celsius. And we want to know how much energy we need to change this 1 kilogram of water into steam. So you go back to specific latent heat, go to the book here. The water has a specific latent heat to vaporization of this much, so 2,300,000 joules per kilogram. L is of water vaporization is equal to joules per kilogram. So we know that we have, so energy is equal to L times M per kilogram. We know it's 1 kilogram. So the amount of energy you need is 2,300 kilojoules, right? You want to add this 2 million to the 700,000. So you see how much energy we need. We need a lot of energy. We're going to reach almost 3 million. So this is 0.7. You need to reach 3 million if you're trying to scale it, right? So this is around 3 million joules. It's going to take this much energy if you're trying to scale it properly, right? You know how to draw a graph, I'm hoping. So if you draw a table of temperature and heat required. So let's say we started with temperature of negative 20 Celsius with a heat of 0. And then to reach 0 Celsius, you needed 4,200 joules. Then to reach, you still stayed at 0. For it to change into liquid, you needed to add 330,000 to this one. So it turned to be 372,000 joules. Then for it to go to 100 Celsius, you needed 792,000 joules. So you can draw a 92,000 joules. This is also 100 Celsius. You can draw this now. And then another question is, how much do I need to heat up the steam from 100 Celsius to say I want to increase it to 120? How much energy would I need? The graph will extend even more here, right? And you can calculate how much energy that is needed, but you need the specific heat capacity of steam. Now, one thing to try to clarify, now you should know what specific heat capacity is, specific latent heat of fusion or vaporization is, and how to use them in order to find the energy, or if you have the energy, so you could have an experiment like I did in the video, where you're trying to find the latent heat during an experiment, but it's not accurate, so you can then have to, you then have to explain why there was an error, because the room temperature was affecting your data in your experiment. But hopefully now you can understand it a bit more and how to use it for calculations. It's basically equations that you need to know and to know which one to use in which example, which situation, and there's always one unknown and you're trying to find it through these equations. So you know the specific heat capacity, but you also need to know the heat capacity, or if you want to call it thermal capacity. So you're removing the word specific. So specific is for each material, obviously, but also for each kilogram. But heat capacity is, say, the heat capacity of something specific. So for the 1 kilogram of water, the amount of energy that you can store in that water is the joules per degree Celsius. So the heat capacity of water for that 1 kilogram, you can store 4,200 joules for each Celsius change. So the more you're adding heat, the more the temperature is rising, each degree rise, you're storing in that object 4,200 joules. So if I'm comparing the heat capacity to 2 kilograms of that water, you double that. So it's 8,400 joules per Celsius. So the amount of energy it is storing inside of it as I'm increasing its temperature is this much. Because I'm not taking into consideration the mass anymore. Thermal capacity is equal to mc. So it's the mass times specific heat capacity. So it's kilogram times joules per kilogram Celsius. The kilogram goes with the kilogram, so you end up with joules per Celsius. So if I'm comparing, say, the thermal capacity of a glass of hot tea of a jacuzzi, comparing it to a jacuzzi, it's the same. Let's say we're talking about the same material, so that you have the same C, but the mass here is a lot bigger than the mass here. Here, it's, let's say, 0.25 kilograms, whereas here, let's say, it's 250 kilograms. It's the same C, so how much heat capacity can this store with with each rise in degrees Celsius? The heat capacity that this can withtake is 250 times 4,200. So the pool can take in 10, 50, 1,000 joules for each Celsius rise. It can store this much energy every rise in 1 Celsius. Whereas with this one, you put 0.25 times 4,200, you get 1,050 joules per Celsius. So the amount of heat that it can store for each Celsius rise is 1,050 joules. Whereas with the jacuzzi, you obviously need a lot more energy to heat it up, and so it's storing a lot more energy. This one will lose its energy a lot faster than this one. This one will need more time to heat up, if you're talking about the same power source that's heating them both up, right? So if you you go into the stove, you take a spoon, but then you also have a tanjara, right? And you add them both under the fire, and you have water in the spoon, and you have a lot of water in the tanjara. Obviously, the water in the spoon will heat up a lot more than the pan, right? Another idea is it also depends on C, on the specific heat capacity. So if you have something with a really low C, then the amount of thermal capacity it can have, or the amount of energy it can store in itself, is less. Okay, so if you're comparing, so we use the analogy of 0.25 kilograms of water. Let's compare it to 0.25 kilograms of oil, right? Or let's say alcohol, because we have the C of alcohol. So C of water, as you should know by now, is 4,200 joules per kilogram Celsius. C of alcohol, 2,500 joules per kilogram Celsius. So, what is the thermal capacity here? So we're trying to find the heat capacity. Oh, wow, capacity of each. It's MC, right? So it's MC here and MC here. 0.25 times this, and this is here 0.25 times this. So here, we know this already, 150 joules per Celsius, whereas with this one, so the amount of heat that this cup can store is 625 joules every Celsius rise. Whereas with this one, it's 1,050 joules per Celsius rise. Obviously, the amount of energy required to heat it up is different, but also the amount of energy that it can store. So the idea is this one, the water, needs more energy to heat up, but it also has a higher thermal capacity because it can store more energy. So the higher your C, the higher specific heat capacity, the more, for the same mass for two different liquids, the amount of heat that a liquid with a higher C can hold is more, basically. So thermal capacity is different than specific heat capacity. Follow north, baby, keep on dancing like you ain't got a choice.